Okay guys, this time I do a little bit more organic chemistry with you. Fischer Esterification was mentioned in another one of my videos. So I thought, why don't we do a video on it anyways, because it's like one of my favorite reactions. It's production of esters from carboxylic acids and from alcohols. So let's go ahead and draw more or less what happens. Let's do the net reaction, and then from there we will show the mechanism. Okay, so let's start by drawing out a carboxylic acid. Now, as I said before, I do all of this on my mouse, so I know the handwriting sucks. I do apologize. That's just what happens with a mouse. It is awful. Okay, so there's our carboxylic acid. I'm going to draw this out in a different color so I can kind of specify what's happening here. Okay, so we need an acid catalyst to help this reaction out. And in this process, okay, I labeled that one as R prime. So we have R prime, we have C, we have O, and then from here we have our O and our other R. And then finally, that H that was on the alcohol is left over, and then we have our OH. Now, of course, because protons can jump in and out of solution, these could be swapped out somewhere along the way with something else, because I mean, you have an acid solution, so you're taking in protons from the acid and other protons getting spit off. So this isn't necessarily true, but this for sure is. We see that the OH has been spit off and the OR has taken its place. Okay, cool. So let's talk about this mechanism and how it works. So the first thing that's pretty important is we are under acidic conditions. So I'm going to use this drawing to kind of get it started, and then we'll move on from there. So we have an acid present in solution. Cool, so we have our H+, which means this oxygen can grab onto it. And in that process, it puts a positive charge on this oxygen. Because the oxygen is carrying a positive charge, and oxygen is very electronegative, does not want that, that means that this double bond is not as strong as it used to be. These electrons are going to spend even more time up top trying to stabilize that positive charge. And that means that this carbon is significantly more electrophilic than normal. Yes, it's electrophilic because you have the oxygen here, you have this oxygen here pulling density away, and these electrons can resonate away. But it's even more electrophilic now because you have this positive charge here that's pulling more density away from it. So that means this is step one. Next step, I'll do another color, and then I'll redraw this so I'm not getting too much happening all together. So the electrons off of this oxygen will come in and attack here, and that causes these electrons to go upwards, and that will get rid of the positive charge. So let's draw out what that looks like. So we have our R prime, our C, oops, my mouse acted up. We have our O, it's bonded to an H. And we have our lone pairs, cool. We have our alcohol, it's trying, my mouse is glitching. I think I have something running in the background that's causing my computer to lag a little bit. And then we have our alcohol. Cool. And from this means we have a positive charge located here. So notice we started with a positive charge. It was on the proton. Then the positive charge got relocated to the oxygen. Then after this reaction, it got relocated to this oxygen. So conservation of charge is still working out here. The next step is a tautomerization. So what happens is, honestly, I can draw this on either one of these oxygens, so I'm going to draw it here. Because, like I said, the OH gets removed. Technically, this O could get removed, but this H, it does not matter which one gets removed, but I'm going to draw it from here. This oxygen comes in and can grab this hydrogen. Because there's a positive charge here, these electrons are going to want to go back. They're going to go back anyways because oxygens can carry that negative charge. These electrons are going to go back and take care of that positive charge. So in this process, we get our R prime, we get our carbon, get our oxygen, get our hydrogen up here. Now we have water here with a positive on this oxygen. And now we have our straight up alcohol, which is fairly stable. Okay. This is a problem. Anytime you see H2O in a reaction, it's either going to be a leaving group or the H is going to be removed from it. We're going to draw as a leaving group, because otherwise, if I remove the H, I just go back a step, and that's kind of wasting my time. So from here, we are going to show these electrons can come downwards to stabilize the leaving of water. So now water is gone. So one of our steps is done. Cool. Or one of our products has been formed. All right, cool. So next step, Okay, so the problem here is we have an H up here. That's putting a positive charge on this oxygen. Okay, so this is very straightforward, very easy to fix. I'm just going to use water to show this. Water can grab onto this, have these electrons go back. Bada bing, bada boom, we're done. The acid catalyst was regenerated because I can see that this makes H3O+. That's why it is a catalyst. It just got reformed. And then what's left over is our final product. And we are done. That is Fischer esterification, but it can be a reversible reaction. Now, in regards to what I showed in one of my previous videos, I showed a compound such as this. This is methyl salicylate. You see it as a methyl group, and you see salicylic acid, but it's like conjugate base. So they call this methyl salicylate. And to show the reverse of this, if you put this under acidic conditions, a proton will attach up here, which puts a positive charge on this oxygen, makes this less stable. Then water can come in and attack right in here. And when that occurs, these electrons come upwards. So let's go ahead and draw that out because that's way too many steps at once. Okay, and we have our carbon, we have our oxygen, we have our hydrogen, we have our alcohol, and here we have water. Okay, so we have a positive charge just chilling on this oxygen, not very nice. This can tautomerize. In that process, these electrons go back to this oxygen. So I'm just going to draw out the ring as a big, I'm going to put a pH. It's not technically, actually it is a phenol, but it's not technically a phenol. But I'm just going to put a pH. I'm going to say pH represents this. This is not true because this is a phenol with an OH. But, whatever. I don't care. I just don't want to write the whole ring out again because that's a lot of time. And I think you'll get the point. Although sometimes I wonder when I help some people with organic chemistry, I see that I try taking a shortcut, and it's like, where'd that shortcut come from? I'm just like, So this pH is just me being lazy and not wanting to draw out a ring, which honestly would have taken less time than me trying to explain why I wrote pH. Okay, so I have a positive charge here. Here's my methyl, all this good stuff. Not very favorable. So let's show these electrons coming back downwards, and in that process, this will break, taking care of that positive charge. If you have a positive on oxygen, something is about to happen. Oxygen does not carry positive charges. And in this process, you see that methanol comes off. Cool. And then, I'm just going to draw out my ring because I wasted more time explaining that than not. Okay, and then we have this product. And we have our OH here. And again, just some water in solution. Comes up, grabs this proton. These electrons go back to the oxygen. And we have salicylic acid. The other compound, just to show you what it looks like, I'm not going to draw its mechanism. But I can, wow, that was bad. Okay. The other compound looks pretty similar. Except right here we have an acetyl group. That's why it's acetyl salicylic acid. And as you see, there is an ester present. And as always, acids and water will split that ester. And we will see the formation of acetic acid, which is this plus an OH. And we will see, again, salicylic acid. Cool, cool, cool. There we go. So yeah, salicylic acid are both from the process of breaking down either methyl salicylate or acetylsalicylic acid. This is wintergreen oil, this is aspirin. They both lead to this final product. This one leads to methanol, while this one leads to essentially vinegar, although likely deprotonated because your acidic conditions in your body aren't like that crazy. I mean, your stomach they are, after that, not really. Okay, so hopefully this helps explain both the process of Fischer esterification, the forward reaction, and the reverse reaction. The mechanisms are just the same thing in reverse. You can Google this and learn a lot of it. But if you need any help with this, let me know. I'll be happy to answer any questions, show you where things are moved around. Organic chemistry is considered a hard class. It's not as bad as you think it is, and we can break it down together to help you out. So this is Fischer esterification, and you can say that this is like the hydrolysis of an ester linkage, because that's technically the same thing. At least this page is. All right, with that, y'all have a wonderful day. Thank you very much for watching.